Okay, hi everyone. My name is Sneha Narayan, and today my project is about analyzing the prominent environmental factors that cause forest fires in the Algerian and Montesinho forests. I'm currently a senior, and my mentor for this project was Kristen. I chose this project because I'm interested in the application of technology to mitigate environmental problems caused by climate change. And I'm currently presenting from the Bay Area in California. This is a brief roadmap for my presentation and what I'll be covering during my presentation today. In the last 10 years, around 82 million hectares of forest have been destroyed by wildfires worldwide. Forest fires are common in hot, dry, and windy areas. They pose great harm to infrastructure and surrounding areas and can cause harmful contaminants, sediments, and heavy metal to leach into nearby water sources. Machine learning models can be used to analyze the occurrence of these forest fires. For my project, I use a random forest classifier to find the factors which most affect wildfire ignition in the Montesinho and Algerian forests. Some causes of wildfire include temperature, wind, low humidity, and less precipitation. High temperatures cause vegetation to dry out, which provides more fuel for fires. Wind increases the supply of oxygen to fires, which accelerates the spread and ignition of these forest fires. Precipitation and humidity can prevent forest fire ignition because it dampens the fuel. Some effects of forest fire include damage to wildlife and ecosystems. Additionally, the smoke from the fires include toxic pollutants, such as PM2.5, which is fine particulate matter, nitrogen dioxide, ozone, and lead. Additionally, forest fires also release carbon dioxide and other greenhouse gases, with global warming and which increase the impact of global warming. With global warming leading to higher temperatures, it increases the risk of forest fires, which leads to a continuous cycle. Therefore, it's important to accurately identify the factors that lead to forest fire in order to be better prepared to combat the fires early on and devise mitigation strategies. There are two types of machine learning models, supervised and unsupervised. For supervised learning, the dataset has labels. And within supervised learning, there are two types, classification and regression. In a classification model, you are predicting categorical variables, and in a regression model, you are predicting a continuous numerical variable. For my project, I created a classification algorithm. In unsupervised learning, the dataset does not have labels, and the model will find patterns in the data. There are two stages to a machine learning model, training and testing. In the training stage, the model is trying to create a function for which the value from that function most closely relates to the true label of the data. And in the testing stage, the function previously created is used to predict the labels of new data. Some common training testing splits between the data are 70% for training, 30% for testing, and 80% for training, 20% for testing. You want more data to be used in the training stage to prevent overfitting, which is when the model too closely adapts to the intricacies of the data. This can occur if there's less training data because then the model is fitting too closely to the small variations of the data rather than being able to generalize for different results. The three key steps for building a machine learning model are defining the features to use. In my case, these were the different environmental factors I wanted to use in order to predict whether a wildfire will occur or not. Creating the algorithm and loss function. The loss function is a method for evaluating how well your algorithm models the dataset. And the final is hyperparameter tuning for further tuning the model and making it more accurate. For the machine learning algorithm I use are decision trees, and more specifically a random forest, which means I use an ensemble of decision trees in order to predict my final results. Some of the positives of using decision trees are that you can identify the feature importance of each features that are used in order to predict the final outcome. They're also fairly accurate for small data sets, can handle numerical and categorical data, and is easy to interpret and visualize since you can actually see the decision trees and see the splits that were made in order to categorize the data into whether a forest fire occurred or did not occur. Some negatives of decision trees are that they're not very accurate for big data sets, they can overfit to the data, they can create biased trees, and can have greedy algorithms. But these last three things can be mitigated by having multiple trees. And so in my case, an ensemble of decision trees, which is called a random forest. My model was trained using the Google Colab CPU. I trained my model on two datasets. One was from the Bejaia region and Sidi Bel Abbes region in Algeria, and the second one was from the Montesinho forest in Portugal. The factors that I used in order to predict my outcome were the fine fuel moisture code, which is basically a numerical rating for the amount of fine fuel in the air. So the higher this numerical rating, the more likely that fire will occur. The Duff moisture code, the drought code, initial spread index, temperature, relative humidity, wind speed, rain, and the month in which the data was collected. I pre-processed both datasets using the Pandas library in Python to make sure that they both had the same features that were used in order to predict the final outcome. I used an 80-20 train test split and the random forest classifier method in order to create my model. I also tuned hyperparameters, and the most prominent one was the number of estimators, which is the number of trees that are used in the random forest. When trained on the Algerian forest fire datasets, my model was extremely accurate and achieved a 100% accuracy. As seen in the confusion matrix, all the data was correctly classified, and the predicted label and true label match for each piece of training data. Here, a 0 represents that a forest fire will not occur, and a 1 indicates the presence of a forest fire. The most prominent factors were the initial spread index and fine fuel moisture code. For the Montesinho forest fire dataset, the model was less accurate, achieving a 55.78% accuracy. As you can see in the confusion matrix, when the true label is 0, which means that there is no forest fire, the model cannot accurately predict whether there is a forest fire and essentially guesses. There is a 50% chance that the model will predict either label. This means that the model cannot find good patterns in the data when there are no forest fires, and therefore is unable to accurately make predictions. When the true label is 1, the model is more accurate in making predictions. The low accuracy could mean that these features are not as predictive for predicting forest fires in the Montesinho region. The most prominent factors in this case were the temperature, relative humidity, and Duff moisture code. Looking at the two decision trees side by side, for the Algerian forest fire dataset, the tree is simple and does not have too many layers. Near the top of the tree, the model is making splits with good criteria, which split the data roughly in half. And all the trees in this decision tree are pure. On the other hand, the Montesinho forest fire decision tree is very complicated and very long. This means that the model likely overfitted to the data. As seen in the beginning, the initial splits, the model isolates samples very early on, and the initial splits of the data, rather than being 50-50, is something like 2% and 98%, which means that the model is not able to generalize to the results. The key features for each data set are different, which means that the results may not be able to be generalized. For the Algerian forest fire, the initial spread index and the fine fuel moisture code were most prominent in making the final decision. This makes sense because a high content of fine fuels leads to ease of fire ignition. For the Montesinho forest fires, temperature, relative humidity, and Duff moisture code were the most prominent factors. The Montesinho forest is located in northern Portugal, where areas experience higher humidity levels. Winters are humid and summers are not overly humid. Due to the variation of humidity, it plays a large role in forest fire occurrence. On days when it's more humid, fires are less likely to occur due to the dampening effect the moisture in the air creates. It's important to understand the environmental factors that are key in causing forest fires so that we can prevent the conditions from reaching a level for which a fire will emerge. Understanding these factors makes it easier to target and prevent conditions from reaching a point for where a forest fire can form. Forest fires are extremely destructive and detrimental to the environment, so it's crucial to prevent them. Some future work includes analyzing more data sets to form a holistic view of the factors impacting wildfire ignition. In this case, the feature importances were different, but that could mean because the climate of the Montesinho forest in Portugal and Algeria are very different, so it's key to analyze more data sets to form a more holistic view of this. Additionally, after understanding these key environmental factors that cause forest fire formation, we can take preventative measures to prevent these conditions from reaching a point of harm. These are my references that I use for the presentation, and thank you so much for listening.
Awesome. Thank you, Sneha. It's great. And one of our audience members actually said that this is very applicable for where she lives. So I think everyone actually, you live in the Bay Area, so I am also based here, and I think we face this every year. So thank you for looking into this. Do you think there are any factors that you could have had access to that you wish you could have, but that could have impacted your presentation? Like, were there any variables that you wish you that were in the data set?
I think the factors that I used were had like a wide variety. It ranged from like weather variables to also some other indices like the amount of fine fuels in the air. If there are any other factors to use, I think maybe also the actually I think the factors that I used were pretty good because I had a wide variety for like many
Gotcha.
different.
Gotcha. Cool. So very, very thorough. Do you think that the results from this presentation or from your model can be used by authorities or like environmental agencies to prevent forest fires?
Yeah, I think definitely for the Algerian forest fires, the model predicted very accurately, so it means that given the data, like the factors that the model found were pretty accurate. So I think that will be good to use. And also, one thing to note for the Algerian forest fires is that the most important features, they're different from what is previously thought of as being a prominent factor. For example, in previous research, most importance is given to like the temperature and humidity, but in this case, for the Algerian fires, we saw that the fine fuel moisture code and the initial spread index was actually what had the most importance. So that could be really helpful.
Gotcha. Very cool and interesting. Final question. Did you come across anything very unexpected while you were doing this project that you didn't think that you would come across?
Yeah, relating back to the Algerian forest fire data set, I kind of expected the top features to be like temperature and humidity, and related to that. And as seen in like the Algerian forest fire data sets, those weren't the top ones. So I was actually kind of surprised about that. And I did like more research into the Algerian area and learned about like the environment there and why fine fuels could be one of the more higher factors.